Starting our last unit in BC Calculus, we're going to be investigating parametric equations. You can look at our learning target at the top of the screen. I can graph parametric equations as well as take derivatives and integrals of them. And first, I think we should address what exactly is a parametric equation, or what are parametric equations. Parametric curves are those where y and x are defined in terms of a third variable. They are dependent on a third variable. We think of that as t very often. Looking at example 1 here, you can see x is equal to the cosine of t, and a lot of times we think of t as time perhaps, but it certainly does not have to be that way. If it was, then your x and your y coordinates would be dependent on a time variable, but it's very important to point out that t could very well be just a third variable in general, not representing time. But let's think about this. T is going to go from 0 to 2 pi. And much the same way we first graph any function or any new graphing situation, we can make a table. You can see I've made tables over here. Certainly you are free to substitute in t equals 0. The cosine of 0, of course, is 1. The sine of 0 is 0. And right now you may most definitely plug in different values, such as pi over 6. Generally we're not going to do that in that regard. But the cosine of pi over 6, of course, you can realize is root 3 over 2, or about 0.866. The sine of pi over 6 would be a half. And maybe what's even more helpful is dealing with the quadrantal angles, like pi over 2. Cosine of pi over 2 is 0. The sine of pi over 2 is 1. You could plug in a pi. The cosine of pi is negative 1. The sine of pi would be 0. You could plug in 3 pi over 2. And the cosine of 3 pi over 2, of course, would be 0, and the sine of 3 pi over 2 would be negative 1. We could very quickly get this graphed out, and as we do that graphing, the t variable is really hidden in this regard. We're just going to be looking at our x and our y. So we can start off with 1 comma 0, maybe right over here. At pi over 6 would be at, root 3 over 2, so at about 0.866, and then up to a half, maybe somewhere around here. But as we continue on, you can see dealing with these quadrantal angles. Plug in, the pi over 2, you'll have 0 comma 1. 0 comma 1 would correspond to this ordered pair. Look at this ordered pair, negative 1, 0. That would be right over here. And then 0 comma negative 1. You might realize that this should seem awfully familiar to the unit circle. And you might not be too surprised to guess, and you could even plug more of these variables in, t parameters I should say, to get this thing graphed out rather nicely. You might guess that we are in fact dealing with a circle. And I want to show you that your calculator can graph parametrics. Look what we can do. We can press mode, but this time instead of going to function, go to parametrics, go to y equals, and you'll see an x1t and a y1t. Well, x, you can see we're going to type in cosine. But of course now we're going to type in a t. And hitting t, you might wonder how you do that. You just press xt theta n. Your x button now represents t. Your y is going to be the sine of t. And we can get this graphed rather quickly. We can see where we're headed with this. We can hit mode to make sure we're on the radians, and we are. When you hit window, your t step, you're going to notice that not only do you have x and y in your window parameters, but now you're going to have t as well. I think a default setting is to have t go between 0 and 2 pi. You might need to change that. But just looking at what has been graphed out, you might wonder if maybe we should just be graphing between -2 and +2, thinking that perhaps this would be sufficient. Do the same thing maybe for y. Maybe type in -2 to +2, and maybe go by a step of 1. Hit graph, and sure enough, you get a circle. Now, that can be wonderfully helpful, and it can be incredibly helpful, but I think what we can definitely wrestle with is, could we perhaps see that we have the equation of a circle in standard notation? And we can. Maybe the most famous trig identity that you're ever going to see will be sine squared and cosine squared add together to get 1. So you can say cosine squared of t plus sine squared of t would have to equal 1. Definitely the most famous trig identity that you're going to see. But cosine of t is really x, so this is really x squared. Sine of t, we just said, was y. And here you have it, the basic equation of a circle, actually the unit circle. You have a center at 0, 0. Your radius, of course, would be a 1. So that's a wonderful way that you could get some immediate confirmation in the rectangular coordinates. And I think it's very important for us to start hearing that. Rectangular coordinates are the coordinates you've been working with all along. They're on the Cartesian plane, or Cartesian coordinates. You'll be having your x and y, and as you work out just your standard notation, you'll have your x squared plus y squared is equal to 1. Well, let's real quickly see what's going on with b. You can see our t is different. We're going to say 0, 1, 2, 3, and 4. And let's go ahead and just begin to evaluate what x is. X is going to be the square root of t. Well, the square root of 0 is 0. The square root of 1 is 1. Here we'd get the square root of 2. Here we'd get the square root of 3. Square root of 4, of course, you'd get 2. Take a look at your y. Plug in a 0. 0 minus 2, you'd get -2. Plug in t equals 1, you'd get 1 minus 2 is -1. Plug in a 2, and you'd get 2 minus 2. Well, of course, you'd get 0. Plug in t equals 3. 3 minus 2 is just a 1. Plug in a 4. 4 minus 2 is 2. And again, moving back to function notation, we can just graph this out in an ordinary sense. You could say, hey, I've got the point 0, comma, -2. It looks like that's where we begin. The other thing is, having t begin and end somewhere, you can begin to represent motion of a particle. You can see then we're going to go to 1, comma, -1. Radical 2 is about 1.4, so it's not quite at the midpoint, but close. Radical 3 is about 1.7, somewhere around there. And then 2, comma 2, we would stop. And so important for us to see that we'd get something that looks like so, a beginning and an end to this graph. You don't want to put arrows indicating that this would continue to change. There's a definite starting and ending point. But let's go ahead and see what exactly is happening here. We can go to y equals and clear this out and type in the square root of t. Down here, I'm going to press clear and type in t minus 2. Now, be careful not to graph this just yet. I think it's very, very important for us to go to our window and realize that our t step, or the t max, I should say, the highest t value you will have is 4. It looks like a -2 by 2 window is sufficient for graphing here. You might want to make adjustments in the future. As you can see, we get something that looks like so. And I think very often more than a few kids might wonder if that's really parabolic. Well, a great question is, could we relay the parametric form to the standard function form? Get a function in terms of y equals some function of x. Well, yeah, we can do that. And it's not that hard to do that. Look at your two parametric forms and solve for t. It's easier to solve for t here. In other words, add a 2. And now substitute in. So you'd have x is equal to the square root of y plus 2. This would be more of a standard notation in terms of x and y. Now we have to be careful if you wanted to solve for y. Actually, this would be a great equation to relate what's happening, especially since we can graph x in terms of y as well. If you wanted to square both sides, you could get misled. You could say, hey, would you look at this? I'm dealing with a parabola. Yeah, it is a parabola, x squared minus 2, like we said. But in all truth, we have to be very careful not to be misled to think that it is a full-blown parabola. We only have the right branch of it, and we're not going to be extending off to that left-hand side. Well, let's take a look. We are in a calculus class. Now that we're looking at curves, I think it's exceptionally important that we go back and we talk about derivatives. And we can analyze slope and concavity just as we did earlier in the year. That being said, the first derivative, I think usually kids are feeling pretty good about that. Like a dy dx, which is still going to represent a tangent line slope. It's always dy dt all over dx dt, a little faint to read here. In other words, take your derivative of y with respect to t, take your derivative of x with respect to t, divide this out, and you'll get dy dx. And that's how you're going to be able to analyze slope, tangent line slope, of course. But of course, second derivatives get used as well. In second derivatives, we have to be so cautious. With the second derivative, please don't think, I put a huge star here, please do not think that it's simply the second derivative of y with respect to t divided by the second derivative of x with respect to t. That type of thinking will get you into a tremendous amount of trouble. We're going to talk more and more about that. Instead, what you need to do to find a second derivative is follow this guideline right here. If y prime is dy dx, and it's a differentiable function of t, what you're going to see is your second derivative of y with respect to x is really going to be this super important form right here. Take dy prime, take the derivative that you just worked out, take it again with respect to t, and then divide by dx dt. Let's take a look real quickly at a first and second derivative and see what that might look like. For number 2, I'm changing this. X is equal to 2t, y is equal to t squared plus 1. dx dt is simply going to be the derivative of 2t with respect to t. That's a 2. dy dt, well, that's just going to be 2t itself. What's dy dx? Well, plain and simply, it's dy dt all over dx dt. So it is 2t divided by 2, which is simply a t. So in other words, if you'd like to find the tangent line slope for any point, plug in that t value, and then you're fine. To find your second derivative, well, it looks like we're running out of time on our video, and I think we're going to have to pick that back up in just a moment. But of course, we're going to go back to this highlighted form.